9.3 Examples of the least square principle. So we've been talking about the least squares principle for 9.1 and 9.2, and we'll continue on with some examples of how we can use this to solve different types of problems that we may encounter in numerical analysis. So the first of these is inconsistent systems. So, curve fitting is not the end of the story with least squares principle, even though that's kind of what we focused on 9.1, 9.2. We can also use it to solve an inconsistent system of linear equations where we have more equations than we have unknowns. So if we're given an n plus 1 tuple and substitute on the left, the discrepancy between the two sides of the k equations is termed the kth residual. Now, ideally, of course, we'd like all these residuals to be zero, so we have an exact solution. If it's not possible, then we can select our x's so as to make. If it's not possible to select the x's to make all the residuals zero, the system is said to be inconsistent or incompatible. In this case, an alternative is to minimize the sums of squares of the residuals. And we can do that by making an appropriate choice of our x sub i's. So, to solve the inconsistent systems of linear equations, we take the partial derivatives with respect to x sub I and set them equal to 0, and that helps us arrive at those normal equations that we've been using. This set of normal equations is a linear system of n plus 1 equations involving unknowns x0 through xn. We can then solve that using Gaussian elimination to get the best approximation of the solution to the system in least square sense. Special methods have been devised in addition to the one that we just discussed. Generally, they gain in precision over this simple approach that we just outlined. One of these is the modified Gram-Schmidt process. A more elaborate algorithm depends on the singular value decomposition of the matrix A. We can also use the least squares principle to approximate functions on intervals. For example, given a function f defined on an interval AB, it can be approximated by functions such as g of x is equal to a sum of functions j sub g of x along with their coefficients c sub j. It's natural to attempt to minimize it by choosing the appropriate coefficients, and that's generally one of the things that we've been doing with this principle. In some applications, it's desirable to force functions g and f into better agreement in certain parts of the interval. And to do that, we can modify the equation by including a positive weight function, which can, of course, be w is equal to 1 if all parts of the interval get treated the same. The weight function 1 minus x squared to the minus 1 half assigns heavy weights to the ends of the interval, to the ends of the function on the interval minus 1, 1. So the minimum function is again sought by differentiating with respect to each c sub I and setting the partial derivatives equal to 0. The result is a system of normal equations, and that's an n plus 1 linear equations and n plus 1 unknowns. And again, we can solve that using Gaussian elimination. Earlier remarks about choosing a good basis, such as the Chebyshev polynomials, apply here as well. Another thing that we can do is solve nonlinear problems. So suppose that we have a table of points x sub k, y sub k, and they need to be fitted by a function of the form y is equal to e raised to the cx. Proceeding as before leads to the problem minimizing the function phi of c is equal to the sum of e to the cx sub k minus y sub k squared. The minimum occurs for value c as defined in the bottom equation where the partial derivative with respect to c is equal to 0. Now, this equation is nonlinear in c. You could think about solving it using some of the methods in Chapter 3 of the text, including Newton's method or the secant method. On the other hand, the problem minimizing the function can be attacked directly. Since there can be multiple roots to the normal equation local minima within the function itself, a direct minimization of the function is sometimes safer. This type of difficulty is typical of these nonlinear least squares problems. So other methods of curve fitting are often preferred if the unknown parameters do not occur linearly in the problem. Alternatively, you could go about linearizing this by changing z equals natural log of y and considering z is equal to cx. And that would work as well. We can also deal with problems that are a mixture of nonlinear and linear. And so suppose we have a table with n plus 1 entries and the functional relationship such as y is equal to a times sine of b times x is suspected. We can use the least squares principle to approximate the appropriate values for the parameters a and b. And according to the minimization or the principle of least squares, parameters should be chosen to minimize the expression, the sum of squares of that function. Now, this can be done by differentiating this expression with respect to a and b and then setting those equal to 0. If b were known, a could be obtained from either equation. The correct value of b is the one for which the two corresponding to a values are identical. So each of the preceding equations should be solved for a and the results set equal to each other. Last but not least, let's talk about singular value decomposition. We covered this a little bit back in 8.2. Singular value decomposition of a matrix is a factorization that can reveal important properties of the matrix and that otherwise could escape detection. Since it yields a complete orthogonal decomposition, it provides a technique for computing the least square solution of a system of equations and at the same time producing the norm of the error vector. So it's a handy-dandy thing. There's actually a constructive theorem, Theorem 1, that tells us how to do it. And let's take a look at how we can actually use this in an example. Now, you can find this example on page 452 of the 7th edition of the textbook. And you'll notice that the problem description actually gives the singular value decomposition. And that's a really good thing since if you look through section 8.2, you'll recall that was a pretty difficult thing to come about. So it's nice that it broke it down for us because there's a lot of nasty radicals. The fractions aren't too horrible, but you can see that these things can get quite nasty quite quickly. So when we do this, we have the rank is equal to 2, and we find the singular values, square root of 3 and 1, and that leads us to obtaining values C1, which are the singular value decomposition multiplied by the solution vector. So the first one is the first column of the singular value decomposition, and the second one is the second column of the singular value decomposition multiplied by that solution vector, and those give us two values, C1 and C2. We can use these two values to put together the solution, along with the inverses of those singular values. And voila, we have a solution that's the same as that from the normal equations. Other items of interest, using singular value decomposition in conjunction with minimal solution theorem. And there's also a discussion on the pseudo-inverse of a matrix and the Penrose properties of the pseudo-inverse. These topics are a bit beyond the scope of the mathematics that we've promised to stick to in this course, but definitely feel free to explore them. I think they're interesting and worth a look. As always, thanks so much for watching.